Hi there everyone. This video, Understanding Deutsch-Josza Constant Algorithm, is extension to my previous upload, that is Deutsch-Josza Algorithm, Classical Coding in Python, as you find it here. And here is the algorithmic description. You can pause the video and look into the description. And here is the black diagram or schematic of Deutsch-Josza quantum algorithm. From the left hand side, we feed the quantum information in the form of quantum states through qubits. Here, the UF is the black box or Oracle Dice-Josza algorithm that promises us UF is constant for all inputs if the outputs are either zeros or ones, or UF is balanced for the 50% of inputs if the outcomes are zeros, and for the remaining 50% of inputs, the outcomes if the outcomes are, let's say, ones, it's balanced. Please recall, quantum Dice-Josza algorithm is a toy problem. It's regarded as a toy problem and it's trivial with little importance. Though it's a toy problem, it is useful in understanding the quantum advantage over the classical computing. So here I'm using the web resource 101computing.net Logical Gate Studios to demo the Dice-Josza constant algorithm classically. This is not quantum approach, but it can be correlated, of course. Here I am using five classical bits or Boolean bits, or digital bits you can say. You can think of using five qubits. Okay, in this image on the left hand side you find five switches in off mode, essentially representing the zero state. The top switch represents the most significant bit or MSB, while the bottom switch represents the least significant bit or LSB. The input is being displayed in hexadecimal numbers on these 7 segment displays here. And this 7 segment display on the right hand side displays the output again in the form of hexadecimal numbers. It uses three input AND gates and five NOT gates, as you already seen here. Needless to say, this circuit is self-explanatory. I just want to mention here that this is one of the combinations I'm using to demo constant Dice-Josza algorithm in a classical way. There are multiple other combinations are also possible. As such, there is no limit. All right, so let me start demoing you the performance of this circuit. So here, as I told you in the beginning, so this is the one on the top is the most significant bit and one on the bottom is the least significant bit. So now the state is read as 000, and this is a, an attempt to explain you the constant Dice-Josza algorithm. And this is our oracle. So this is the oracle, one of the combinations of the oracle. And the combination starts from the middle of switch and the NOT gates followed by the AND gates, the three input AND gates. And on the top right hand side we read the output. So now for all zeros, as you see here, so the output is 0, which makes sense, which is okay. That's exactly what Dice-Josza is promising. Now let me change the input to 1. So I am turning on the least significant bit here. And now the input reads 1, but the output appears to be still 0. Now let me change it to 2. Output is again 0. And now 3. Apparently input is 3, but the output is 0. Now let me change it to 4. Output is 0. Now 5. Output is again 0. Now 6. Output is 0. Now 7. Output is 0. Now let me change it to 8. The output is 0. 9. The output is 0. And 10. The output is again 0. 10 is actually in hexadecimal number, it's alphabetical A, which is itself is a hexadecimal number. With 0A, which is 10, the output or decimal 10, the output is still 0. And now let me change it to 11, which is B. Apparently the output is again 0. And After 10, it's I think it's 11. Now a I think, okay, let me change it to, now this is, um, yeah, this is 8 plus 3 11, which is b, and output is 0. Now 12, which is 8 plus 4. So so this is uh, 12, which is c, and the output is still 0. 13, which is d, the output is still 0. Now 14, which is e, output again 0. And now let me change it to 15, 15 1 5. F, hexadecimal f, which is 0 again. Now 16, which is 1 0 0 0 0. Apparently for 16, which is 1 0, the output is 0 again. 16. Now 17, which is 1 1, output is 0. And 17 18, which is 12, output is 0. 19, output 0, which is 1 3. 1 3 is equivalent of 19. Now 20, now let me turn on, the output is 0, which is 1 4. This is 14. Now 15, maybe I need to yeah, 15. Now that is 0. Now let's change it to 16, which is 16 plus 6 22. So with the input 22, with input 22, the output is 0. 22 and 23, 23, yeah, that is 0. Now let me turn on, this is 24. For the 24, the input is 0. We are actually walking through all 0 to 2 to the power of 5, which is 32. So we started from 0, and we are actually walking up to 31, which is all switches turned on to see the performance output. And for 18, which is 24, the output appears to be still 0. Now let me change it to 25, which is 19 1 9, actually output is 0. Now this is 1a, so which is 16 plus 10, 26, the output is 0. And let me show you for 27, which is 1b, output is 0. And now further 1c, which is 16 plus 12 28, the output is 0. Now just show you quickly, this is 31 or 1f, output is 0. So what I'm trying to demonstrate here is that to prove that this algorithm is constant, I have to perform all iterations starting from 0 to n, where n is 2 to the power of n. In this case, it's 2 to the power of 5, which is 32. So to prove to prove the promise, or to verify the promise made by dice that this circuit is constant, I have to walk through all the combinations to confidently tell that this circuit is constant type circuit. And in the big O notations, or the time complexity for this circuit is big O(n), which is order of n. Classically, or in a Boolean way on all digital computers, to confidently verify the promise made by Deutsch-Josza, the tie problem, so one need to at least perform 2 to the power of n over 2 plus 1 additional iterations to confirm the promise made by Deutsch-Josza. So essentially, in a worst case, on a classical computer, or let's say on Turing machine, we have to perform n iterations, which is 2 to the power of n number of, where n being the number of bits or qubits we are using. And in the best case, of course, it's 2 to the power of n over 2 plus 1. Larger than n, it takes more time to solve the problem. And ironically, on a quantum computer, it takes just one iteration to solve, or let's say to prove the Deutsch-Josza's promise. That's the quantum advantage. And here is the another schematic. The difference here is that all outputs are expected to be 1 here. In the previous case, all the outputs were 0. And this schematic, regardless whatever you feed, from 0, ranging from 0 to 2 to the power of n, which is in this case 2 to the power of 5, 32, the outputs remain 1. And the output should show us 1f, which is 31 always. So let's test that. Okay, now let me change the state, input state to 0. Apparently the input state here is 0, and we are reading the reading is 0 here. And we see 1f, which is equivalent of 1 all ones. That's why you see here all wires, or let's say all the lines, are in pinkish or magenta colored, or being highlighted in magenta. Now let me just this time I'm going to just perform 2 to the power of n by 2 plus 1, which is 32 half 32, which is 17 iterations. So in these 17 iterations, I will confidently say that this circuit is actually making its promise, or Deutsch-Josza is properly being verified, instead of performing all 31 iterations. So let me start from 1. It's again all ones, which is 1f. Now 2, no change. 3, no change. 4, no change. 5, no change. 6, 5, 6, no change. 7, no change. 8, again all are being read 1 1 1 1 1. 5 ones, which is 1f. 9, 1f. 10, 1f. Now let me try for 11, which is 8 plus 3, 11. So 1b is actually 11, which is equivalent of 16 to the power of 0 plus b, which is actually okay. So this is 8 plus 3, which is 11. Right, so which is F, 11, and now 12, which is 8 plus 4, so 12, which is C, 0C is 12, and the output is 1F. 13, 1F. 14, which is 0E, again 1F, which is all ones, and 15, and I think this is, okay, 0E, and 0F, which is 15, 1F again. Now 16, to perform 16, I will go with this one being the most significant bit on the top being 1. So 10, which is 16 in hexadecimal, or 10, which is actually 16 in decimal. Hexadecimal it's 10, and apparently this is 1F. Now I'll just perform 1, because 2 to the power of n by 2, which is 16, and to confidently tell that this algorithm is working properly, or the promises made by Deutsch-Josza are fulfilled. So I'll perform the last iteration, which is 17th. Apparently this is verified. So the point here is, it takes at least 2 to the power of n over 2 algorithms in best case, or 2 to the all n iterations, to verify the promise made by Deutsch-Josza that this circuit is constant. This is valid in classical computers or in Turing machine, but the advantage with quantum computers, or let's say the quantum equivalent of Deutsch-Josza algorithm, to prove this promise, we just need to perform one iteration. So if you keep on adding the bits here, the number of checks or balances to verify the algorithm works is increasing, linearly increasing in fact. So that's the quantum advantage here. So in my upcoming video, I will demonstrate a Qiskit based circuit to prove or to verify the Deutsch-Josza algorithm quantum mechanically, or quantum computing way. Okay guys, that's about understanding Deutsch-Josza quantum algorithm classically or in a Boolean way. Please look into description for details, content, and information along with links. If you have enjoyed my presentation, please like, comment, share, subscribe to my channel for more such content. Thank you very much, guys. Until next time.